Okay, good afternoon, everyone. Let's get started. Oh, excuse me. I just wanted to check, is this working? Can you hear me well? Okay, great. Before we dive into our next topic, I want to remind you that the first homework is due tomorrow. And then immediately after, we are going to release a new homework that's going to be due 2 weeks from now. So now the period for your assignments is going to shorter to 2 weeks. I want to remind you that what I said in the first lecture, that doesn't mean that these upcoming assignments are easier than the first one you had. We gave you a little bit more time just because, you know, maybe you needed to get into the machine learning basics, so slower pace was fine. So have that in mind. I again recommend that you just start immediately, see what's there, and then, you know, assess for yourself how much time you will need based on your, you know, machine learning knowledge and the Python program. Are there any questions? There has been a lot going on in Piazza. TAs have been answering your questions well. I didn't need to intervene, but still, are there any questions about that, given that the deadline is tomorrow? Or about logistics of the class in general? Anything about the content we have covered before? Any remaining questions that we didn't answer? Yeah.
I have a question about like the loss for the logistics.
Mm-hmm.
So when you're doing the graded descent, you loop for each epoch, you loop through your data, and then depending on what it's classified as, do you use a different loss function? Like I know in class we calculated the grade for the plus instead of zero. If it's zero, do we use a different loss function? Is that correct?
Yeah, that's a good question. Let me see, maybe I can pull out the equation. Actually, we will come back to the losses again. So maybe when I show the equation again, we can come back to this question. But in general, you will have a form of your loss that kind of handles both of these cases. You don't have in your code like loss for positive, loss for negative. Rather, you have one equation that covers all of the cases. And today we are going to talk about multi-class classification, where you have more than just two options. So you might have, I don't know, topic classification, for example, is an NLP task, and you might have thousands of topics, like in Google News, for example. And then we don't want to define thousands of loss functions, right? So we will find a form of this loss equation that kind of covers all of these cases. Yeah.
On the assignment, does our better featureizer have to actually be better than the other ones?
What did we say in Piat? This question was asked multiple times, right? No, yeah, I'm just kidding. Yeah, so for the better class, for the better feature, you need to have, you need to explore and then report whatever was the best among those you explored. But those do not necessarily need to be better than the unigram or the bigrams that you have used for your logistic and perceptual. Yeah. And sorry, I'm just joking. It's no hard feelings. Okay, any other questions? Okay. So just a quick recap of what are we generally talking about in this first part of the course. We are talking about how to build these simple NLP systems, and we are focusing on a classification setup where we have some text and we want to classify it. And we kind of divide these two processes into producing a representation of our text. And then the second part is take that representation and feed it into a function that will give you the prediction. And this function, we don't know it a priori. We are using machine learning, which means that we are learning the parameters of that function. And we have talked about splitting the text, how, you know, involved it can be. We have talked about producing simple features. And last time we have talked about word embeddings, which are these dense, short representations of input tokens. And as our examples of the learning algorithms, we have covered perceptron and logistic regression. So today, what we are going to focus on is, again, this part where we are going to talk about another type of these functions, namely neural networks, that you probably have heard of before at least as a buzzword, right? So today's lecture is going to be more on a machine learning side. We won't talk much about language properties, and a lot of what we are going to talk about today is also going to transfer to other modalities such as images. So this is one of those, machine learning lectures. Okay, so as a motivation, I want to remind you of this example we have seen when we were talking about perceptron, where in this example, do you remember what the issue was? Yeah, exactly. It's not linearly separable. And I said at that point, okay, but if you decide to change your way of presenting your features and instead of unigrams, you are considering bigrams, then you would turn this space into something that looks different and is actually linearly separable. And this is actually motivation behind neural networks too. Neural networks transform the data into a nicer latent or hidden feature space. By nicer, there are many ways we can characterize nicer, but in this specific example, it means linearly separable. And latent or hidden means you're turning these vectors you started with that might have been interpretable, such as you understand that in the ith dimension of that vector is the count of the token that's ith token in the vocabulary. But now when you do this transformation, you kind of lose that nice interpretations, and in that sense, they are hidden or latent. So mathematically, what does this mean? This means you will take some matrix W. You are going to multiply this matrix with your feature vector. And what this is going to do is going to kind of make a linear transformation of your features. You might scale them differently, and it might shift them around. And then you have this nonlinear function. Nonlinear function will kind of make your features that might have linear relationship with each other nonlinear. So when we make a prediction like we have been doing before with the logistic regression, now what has changed is that instead of multiplying our weight vector with the feature vector f of x, we are multiplying it with this transformed feature space. So not much has changed. We are just taking our initial feature space, changing it into, transforming it into another space, and then everything stays the same. But let's go over this a little bit more. So I said when you are multiplying your feature vector with this matrix W, you are going to do this transformation where you are going to, you see how, maybe when it starts again, I will tell you what exactly. So here you see how the scale is changing and the things are going to now shift. So we have a linear transformation and then this shifts. Remember, I have said before, I'm not going to drag the bias term around. I'm always folding it into our weights. So here by W, we have, you can also think about it as W X plus B. And the B comes from, the bias term that I folded in. And G is a nonlinear transformation. So you see in this final step how these things are becoming a little bit curved. Okay, so if we are doing that, then if we have a linear classification, here we have two sets of examples. Those that are on a blue line, they correspond to one class. And here we have on the red line examples that correspond to another class. If you do any kind of linear classifications, you are going to end up with errors. Here we have, you see here is our decision boundary, and you can see how examples are going to be, for example, here misclassified and over here as well. So what neural networks are going to do for us, then I'm going to learn this nonlinear boundary. So we will get the boundary that looks like this, and that works now, right? Everything is properly classified. And here we are looking at the decision boundary in the original feature space. However, if we are going to visualize decision boundary in this transformed space, you see that these lines are kind of now totally transformed, right? The whole space is not this nice grid anymore. So your lines are moved around as well. And now you actually can linearly separate them. And that's the idea behind this nonlinear transformation. Is this intuition clear? Okay. So yeah, what I have said before, we make this nonlinear transformation, we made only a single one of them, right? But you might have heard about the term deep learning. What this is referring is to a very simple idea where you take this transformation I have described, you get some kind of output, and then you take that new feature representation, and then you transform it again. And you keep transforming it until you transform your initial space so much that things have now separated. So the depth here comes from this stacking of these nonlinear operations. The more of these you stack, the deeper your neural network is going to be. If we have stacked L of them, we are going to say that we have a neural network of the length of the depth L. So this is what deep neural networks are, opposed to shallow neural networks, which might have 1 or 2 layers. Honestly, we don't even talk about shallow neural networks much anymore, because more or less all the neural networks today are very deep. And the subfield of machine learning that deals with deep neural network is called deep learning. Okay, and this is again just another visualization of how this is an example where this problem has been turned with a 4-layer neural network into something that then becomes nicely separable. Okay, deep depth of the neural networks, that's, I suppose, clear. It's a pretty simple concept, right? Okay, so you might now be wondering, what are these nonlinear functions? And there are a few of them that have been proposed in the field. Very often we have seen sigmoid, which we also refer to as a logistic regression before. We have, here we don't have 10H. 10H looks very similar to sigmoid, but you have saturation at -1 and 1, and in 0, you go through 0. Then we have very important one, which is unfortunately not super visible here. It's ReLU, where for negative values, you have 0, but for positive values, you have identity. You might be wondering, how is that nonlinear, right? Because it's piecewise linear. But when we do this stacking of these operations, more you combine these piecewise linear functions, you're gonna get nonlinear transformation. And there are more newer proposals like Swish and ELU. They obviously have different properties. And for us right now, it's not really important to understand how all of these properties might have, downstream impact. There's a whole course on deep learning. So here we are just going to go over the basics. You can think of the nonlinearity as a ReLU. It's the most common choice today, but this space is constantly evolving. And usually there is a more theoretical heavy paper that will be published in the top machine learning venue like ICML or NeoRIPS, and they'll say, well, we have these, we believe this is going to be a better nonlinear function due to these properties. And then someone maybe takes that nonlinearity and embeds it into a big, neural network. Like, for example, Meta has used new nonlinearity for training a Llama 2, which is a new pre-trained language model. And then that nonlinearity kind of becomes what people use. So yeah, there isn't really, it's kind of evolving space, but not super fast. ReLU is still a very common choice. Questions about nonlinearities? Yep. Computational expense. Yeah, I mean, I don't think none of them are really expensive. These are all very basic, functions. You can see that there isn't anything very special about them. It's all about basic mathematical operations such as exponentiating or, dividing things by something else. So none of them are particularly expensive. But then when you look at the ReLU, it's really simple. Like you don't change anything if your value is positive, and if your value is negative, you set it to 0. So it's very simple. And then, yeah, later I will mention where some of these properties, come into play. I won't go into the details. It's going to be related to stochastic gradient descent and gradients. For now, let's leave it at this. Okay, so now we come to the multi-classification problem, which is a little bit digression right now for a moment. So bear with me. When we talked about logistic regression and perceptron, we embedded all of the discussion in a binary classification setup where we have only 2 classes, positive or negative sentiment, for example. But in many machine learning problems, you will not have a binary classification. Rather, you will have multiple classes. Even with sentiment classification, you can have positive, negative, and neutral, right? So how do we deal with the multiple classes? And there are basically 2 ways for today. The first way is what matters. One way to deal with the multiple classes is that you have a separate weight vector for each one of your classes, which is denoted with WI here. With logistic regression, we had only one of these, right? So in this case, when we have multiple classes, we are going to have multiple of these weight vectors. We are going to then, for every possible label in our output space or a label space, compute what's the product of its corresponding weight vector with the feature vector. And whatever turns out to be the maximum dot product, we will say, well, then the corresponding label is the predicted label. Okay? So that's one way, the way we are gonna embrace today. And the other way is that instead of having a separate weight vector for each one of your classes, you have a separate feature vector for each one of your classes. So here that's denoted by f of x and I, not just f of x. Now it's also a function of the output space. And you have the same weight vector for all of these. Again, you will do the dot product and choose the label that has the maximum dot product. This is not really what you will ever see with neural networks, because neural network, the deeper they become, their training becomes very slow. Like for our experiments in our NLP group, take at least a couple of hours, usually a couple of days as well. So you don't want to rerun anything. And here it means you will need to rerun your whole computations with the different input features. So with neural networks, this is not something you're going to do. You will have instead different weights for your labels. Okay. Is this clear? All right. So now we are going to talk about one super important component of neural networks, which is going to be softmax. And before that, here we have an equation, which is the probability of our label being an ith label in our output space. Also, before I didn't emphasize maybe enough that we call the set of possible labels output space or label space, or label set, or whatever. So we have, let's say, m possible options. The probability we are going to have the ith one is equals to the e to the power of the dot product between the weights corresponding to that label, to the ith label. So here, see, we have subscript times f of x. And now what we are using to divide that term has changed from our binary logistic regression. Here we have this sum over all of the possible labels and the e to the power of the dot product of the weights of those corresponding to each one of these labels times f of x. And basically the idea is the same as before. We want to have the notion of probability here. So here we are dividing by this term to normalize these values, such that in the end, if we sum up probabilities for each one of the possible classes, we are gonna get 1. That's what this is achieving. But otherwise, you have a similar form to what you had with the logistic regression. So this is a little visualization of what's going on. So if we had these dot products, here -1, +2, -4, then what this function is doing is exponentiating and normalizing, but effectively what it's doing is squashing this value to be between 0 and 1, which gives us this notion of probability. So if the dot product for our second class was very high, that class will have very high probability. And that's what we want to achieve, right? That's the goal. This operation, exponentiate and normalize, is formally known as softmax. And it's very, very similar, and it has a connection to the logistic function we have seen before. It's just the case that before we didn't have multiple things in our input. It was a function of just a single variable. Softmax is a function of multiple variables. What softmax does, it takes each one of these values and does this exact operation, exponentiates and normalizes, which has that squashing effect. So similarly to logistic regression, where we had some value and then that value turned into that sigmoid-looking function, this is basically what's going on here as well. Okay, so questions about this part? Just to reiterate, we have a softmax that's a mathematical function. It's a thing that exists regardless of neural networks. And then here we have a form of softmax function, where in place of these inputs z, we have these dot products, where each dot product is a dot product of the weights corresponding to a particular class times feature vector. Because what we are trying to do here is we're trying to find to determine something like this. We're trying to see which one of these classes will have the highest probability. So also this connection between the multi-class logistic regression and softmax might come handy to know. Like I said before, we are introducing logistic regression because it's going to be an important part for many of the machine learning algorithms, including neural networks. And that's kind of what we are getting here as well. And the only difference I would say between multi-class logistic regression and softmax is that, you know, this multi-class logistic regression, the formula for these probabilities is an instance of a softmax with a particular values in the input that were designed to achieve something, namely that high dot products between weights and feature vectors correspond to high probabilities. Okay, I don't see any questions, although I don't get the sense of like this really hit the spot, but hopefully more we talk is gonna become clearer. This is the same thing I have shown you in the previous slide, just written in a compact way. So we have our output space is going to be a vector. Let's say you can write it as a set, whatever, it doesn't really matter. Here I wrote it as a let's say list of m possibilities. And this probability is the same probability we have seen in the previous slide. And now we are going to write basically this in a more compact way. We want to have the probability distribution over the output space. So we want to have distribution over these values. And this can be written if we place each one of these vectors, weight vectors corresponding to each one of the classes, to be one row in a matrix we are constructing. So we are constructing matrix WO, where we take each one of these weight vectors and we place them, their transposes to be rows in this matrix. So this whole equation then can be written as the product between WO times f of x and taking the softmax of the corresponding vector. And then what your prediction task is to find the label II that maximizes, that's the maximum in this vector that we get as the output of the softmax. Okay, is that clear? So not much has changed, just the way we write these things has changed. Instead of writing each one of these things, each one of these probabilities for each class, we are writing a distribution over the output space using the matrix vector product. But underlying computations in these matrix vector products are the same as the computations we have in each one of these individual probabilities. Okay, yeah, maybe it's hard to immediately grasp it, but if you try to write it down, you will see what I just said is truly the case. And this brings us actually to our first neural network. Very easy from just logistic regression, right? We have our output space, this list of possible labels. We have our weight matrix, output weight matrix, which in each row has a weight vector corresponding to each of the possible classes. And again, we have this way of computing things, but what has changed from the previous slide here, we have with the multi-class logistic regression, we are working with our original feature space. So these might be our embeddings, they might be our presence or absence, very sparse vectors, whatever we had in the beginning. With neural networks, we have said we are going to transform that space into something more useful. So the only thing that has changed is that instead of f of x, we have the transformed f of x, which is transformed by multiplying it with a weight matrix W1, and then applying nonlinear function to this matrix. When we are applying nonlinear function to a matrix, that means we are applying this nonlinearity to each value in the matrix. So 10h, for example, of each one of the numbers in the matrix. So in the end, you again, vector here, matrix times vector product gives us a vector. Apply nonlinearity, you will again get a vector. And then you multiply that with the matrix, and then you again get a vector. Softmax applied to a vector gives you again a vector. And from that vector, you pick the argmax. And I will go over this one more time with the visualizations. So we start with our n-dimensional feature vector. We then multiply it by matrix W1. This matrix will be of the size d times n, where d is the dimension of the new space we are transforming to. So I don't have great examples for the numbers. For example, with pre-trained language models, this might be 768 dimensional vector, and then the next operation might turn it again into the same dimensional vector or something alike. It's not going to be widely different. Now you get a vector from this multiplication, and you are going to then apply nonlinearity to this vector, which means you're just going to apply it element-wise. So this will give you the transform vector. So, in those visualizations, we had nice spirals, and then they were kind of bended in this new space. Yeah, this is basically given in this vector. So if we had recorded points on the spiral and then make the transformation, what we would get here are the coordinates of the newly transformed space. Okay, so now the next step, we are here. We have transformed our feature space. And what follows is basically similar to multi-class logistic regression. Now, instead of applying logistic regression to f of x, you're applying it to this new vector g of W1 times f of x. So that means you are going to multiply it with your output matrix. And this output matrix will be of the size m times d. Because remember, it is constructed by taking rows, taking weight vectors corresponding to each one of the classes and placing them as rows. And remember, our weight vectors in our logistic regressions are in the same space as our input examples. So if we are working in a d-dimensional space, our weight vectors are going to be d-dimensional too. And if we stack them row-wise, m of them, we are going to get m times d matrix. So this is where we are. Now we are doing this matrix vector multiplication. When we do that, we are going to end up with a vector of the size m. And now we are applying softmax. When we apply softmax to an m-dimensional vector, we are going to get m-dimensional vectors, but the values are going to be squashed between 0 and 1. So all that has changed is transforming those dot products into values that are between 0 and 1. And if the value of dot product was very high, the probability will be very high, close to 1. If the dot product was really close to 0, then the probability is going to be close to 0. So this is our distribution over the output space. And now we are taking the argmax. We take that vector. We find which one of the dimensions has the highest value associated with it. And if it's, let's say, second dimension in this vector, we are going to say second label in this output space is the predicted one. That's what argmax does, opposed to just max. Had a question?
Can you tell where the weight matrix W1 came from?
Yeah, that's a great question. As always, I am kind of building up this. This is how you predict, but I don't tell you where these numbers come from, right? So these numbers over here, they are first randomly initialized, and then we need to learn them, as always with machine learning. So these values, every single number that's in these matrix W1 and WO are our parameters, weights, coefficients. I keep using the word parameters or weights. And these, we don't know them a priori. That's what machine learning is for. Machine learning then takes the data and tweaks this value such that the loss is minimized. We can start with randomly initialized weights, but then later when we learn about pre-trained language models and pre-trained neural networks, that's the key idea behind pre-training. These weights are not random anymore. They have come from another model that's been trained in some fashion, and now they're not random numbers anymore. They come from that model. I also want to go over a few terms. So when you do this transformation, you produce a hidden representation. I'll come to your question as soon as I go over these terms. So here, whenever you make, in this matrix vector multiplication, this vector, we will say this is a hidden representation. And at any layer, you can get hidden representation, but usually when we make the final prediction, we are going to make it on the using the representation that comes from the layer that was right before the output layer. So that's going to be your hidden representation. So if someone say, oh yeah, use hidden representation, that means take the output of the almost final layer of a neural network to be a representation of your input. The values you get here are often called logits, these values that are not normalized. And then when you apply to softmax to them, people are going to use word probability. And although there is that notion of probability, it's not exactly probability. And I will come to that whole topic, hopefully at some point. But basically what it means that this probability doesn't tell you that if the probability is 0.9 for a label, it doesn't mean that the model is 90% is going to be correct in 90% of the times in predicting that label. But people are going to use probability to describe what's in these vectors. And this whole pass from the input to your prediction is called forward pass. You had a question, I believe.
Why are we doing the W0 again?
W0 is your output matrix. It means you are gonna, you have your feature vector. Remember with logistic regression, you had some feature vector. Here, your feature vector is this now hidden representation. And now you need to decide what is going to be a label that's, the label that we predict to be the case for this example. And with the logistic regression, we had only one of these weights, which would be just like one row vector. But here, because now we turn into multi-classification problems, we instead of having just a single row vector, we have a matrix where each row in this matrix corresponds to the possible label. So it's just a generalization of logistic regression. You turn that weight vector into a weight matrix.
Here, M is our number of output classes, right?
That's right.
And N is the dimensionality of the feature vector. So how do we choose the number D, like the number of dimensions that we transform?
Yeah, so it's a hyperparameter. And before models were pre-trained, it was an important parameter to set. And then as every hyperparameter, there is some notion of what are the good values to choose. And they also depend on what's your size of your input feature. Like if N is 300, you won't now transform it in a 30,000 dimensional space. Maybe you'll pick something up to 1,000. And with other types of neural networks, for example, convolutional neural networks, there was an idea of like, you want to maybe reduce the size, then increase it. This might have some benefits and so on. But right now, honestly, it doesn't really matter because you are going to end up using pre-trained language models. And with those, you cannot change a thing because you need to use, if they choose that D is going to be 768, you can't choose, and you want to reuse their matrix, then you can't do anything about that hyperparameters because you are stuck with their matrices. So today we don't really pick those hyperparameters anymore.
Can we say they were determined empirically?
I would say, yeah, a mix of initial theoretical exploration with very small networks had led to some insights about maybe you don't want to have, as I said, like very weird ratios between your input features and your hidden feature number. So there was initially like some even theoretical insight, but a lot of these things and in the end are very empirical. Yeah. And they become less empirical the bigger your model is and more pre-trained is, because when you have a single layer neural network, you can run gazillion of these there. That's quite fast. But if you have, and today we have networks with dozens or hundreds of billions of parameters, then that exploration becomes way too expensive. Yeah. Okay, so yeah, I mean, it's honestly been a while that I trained one of these because we are so dependent on pre-trained models. So I definitely published a paper where I use one of these, but now if you ask me what's the number I have used in my paper, I'll be like, I really literally can't remember. So yeah.
This better for networking with that higher D dimensions?
Not necessarily. So you don't want to increase D to be large because then you have more parameters to learn. So here, if you had, I don't know, 3 input features and you turn it into 10-dimensional space, you would have 30 features to learn. But if you had instead of 10-dimensional space, 1,000-dimensional space, now you have 3,000 parameters to learn. And that can cause, if you have very little data and you start with randomly initialized weights, that can lead to overfitting because now the more parameters you have, try to imagine them as having crazy polynomials and they can do all sorts of things.
It's higher flexibility.
Higher flexibility for sure. And then you might run into overfitting problem. So you definitely don't want to have just a ton of parameters, but it is true that more parameters have also this flexibility can be nice if you have indeed a very complex problem and enough data to learn from. Yeah.
So does the softmax function return like a vector like each of the probabilities of each of the labels? So then when you say probability of y and x, you just go to like the y or like the corresponding row or element in the thing returned by softmax.
Yeah, so may I maybe just rephrase your question? So you're wondering how what's exactly done over here? So for that, I think it might be useful to go back to this equation over here. So in this case, these z's are, this z vector is the product of our output matrix and our hidden representation. And we are applying softmax to this vector z, which means we take each one of these values in these vectors and do this transformation, which is exponentiate this number and normalize it. And it will turn it into something that's between 0 and 1. And we do it for every value in the vector z. Okay, so this is our forward pass. Any other questions about this? Oh, yeah.
Go back to the Softmax.
Mhm.
What do you want to differentiate?
Why do we want to exponentiate and normalize this? Because we want to have this notion of probability in the end is the reason why we are doing that. Yeah.
Can you define not just numbers? Like what do you want to do?
Yeah, so you could conceivably do that. We are going to use that. Remember when we were deriving the probabilities for logistic regression, we want those operations that we were deriving there. So go back to those derivations in the lecture number 2. And there we did rely into having these kinds of nice properties. So this is, in the end, you could take the argmax of your logit vector, which is not normalized, and you would get a prediction. But the learning, which comes, what I will describe next, depends on having these values that are between 0 and 1.
Is there a relation between this multi-class and binary class logistic relation where we add like 1 plus e to the power?
Yeah, I mean, it is very, very similar. I mean, the intuition behind it is very similar. And I do believe if you set your, if you can write your binary logistic regression as the multi-class logistic regression and use this formula. If you set your vector for weight vector for the negative class to be 0 vector. So that's your, that's your weight vector for the negative class, and whatever you had before for your positive class, you stack them together in a matrix, you get the same thing. Yeah. But I don't think that's really important. I think this notion of what we are doing here and these shapes of these functions, that's what's important. Yeah, like high dot product corresponds to high probability. Okay, so now, let me see what's next. Oh, this doesn't look great. Let me do this. Okay, so this brings us to our application of feedforward neural network to problems with text and how you could do that. The easiest thing you could do is to use, first of all, our embeddings. We have decided that's nicer. And especially now when we think about this weight matrices, if we had very sparse vectors, we would end up with very sparse representations here, and it might cause very big learning problems. And so we start with our dense vector representations, and you have 2 routes to go here. You could, and people have done this, you can randomly initialize your vector token embeddings. So you can decide, I'm going to set my dimension n to be 300, and I'm going to start with randomly initialized values for my word embeddings. And then this feature vector becomes yet another weight matrix or weight vector that you need to learn. So you could definitely do that, and people have done that before useful off-shell token embeddings had appeared. Much better alternative is to use someone else's embeddings that are already trained. And then, as we have seen in the past lecture, they already capture some notion of semantics, lexical semantics, as well as relational semantics. So why don't we just use those, because they already capture what we need? And you can do that. So for example, you use word2vec, and I don't know exact dimension it has, but let's say it has 300. And you could then keep them fixed. That's how we say when you do not treat them as a parameters you learn. So just the way I have presented over here, those are not learned parameters, and you do everything next in your forward pass. Or you could start with those off-shell word embeddings and treat them as a parameters. And Later on, we will refer to this idea as fine-tuning. You have these representations which already capture important aspects of a language, but then they are maybe not specialized for your task. Maybe for your task, such as sentiment classification, your representation really need to capture in these vectors the presence of sentiment-bearing words. So that must somehow be salient feature in that vector. So you might start with the off-shell embeddings, but you might decide to also fine-tune them, treat them as the weights. And yeah, of course, we don't start with a word and classify a word. Maybe sometimes we do that, but often we start with a full text, such as a movie review. So what to do now, because you have token embedding for each one of them, you can average the token embedding of all of the tokens that appear in your input text. And then you will get a single vector that represents the whole sentence or whole paragraph. And that's going to be your input feature. Okay. And this is when, we started to do these things. I believe maybe one of the first papers that have done that is from Iver et al. 2015. And they refer to this as deep averaging network, where you take these, Predator is a masterpiece, talking about the Predator the movie. You have four words here. You take each one of their word-to-vec representation, you average them, and then you do what we have talked about in this lecture. This is opposed to something that has been in fashion at the time called recursive neural network that didn't really survive with time. We don't really use them anymore, where in recursive neural network, the idea behind it is, you want to kind of, language is inherently compositional, so you might want to try to build the representation of phrases similar to a tree, not exactly like constituency tree that we'll learn later on in this class, but like you are building up these representations. And this paper has shown that, you don't really need to do that. You can just average the token embeddings, have this bag of vector representation, shove it into your network, and it works well. So today, because things are kind of working like this, we might not come as a surprise if you know more about this topic. But at the time, this idea, you can strip away so much manual intervention about what's important in a language, represent tokens with these vectors whose dimensions you don't understand, and just average them and do this transformation and have way better performance was really major. Like in this era, after it has been shown that works for image classification in 2014, and then it works for language, it really was when this whole new wave and the end of deep learning winter has started. And this is basically going to be your homework too, where you are going to implement this one for the same task you had in your homework one. Okay, are there questions about this? It's a very, again, simple idea. There isn't much to it. Sometimes it's, it's important. So I want to be like, this is important, but it's so simple that it might seem like, why am I making the big case out of it? Yep.
The previous slide, the FX is the pre-trained embeddings, right? Which you have put in.
Yeah, you can start here with either word-to-vec embeddings, GLAV embeddings, whatever other embeddings you know of, or you can start with randomly initialized one and treat them as a parameters to learn. If you are learning, if you are using the pre-trained one, then here this matrix is going to be, you can choose D, but you cannot choose N. But when you start with randomly initialized one, you can choose N because you are not stuck with anyone else's embeddings. Okay, and now I remember that I never answered your question really specifically. How do we change these weights, right? How do we learning? I think by now you might guess it might have something to do with stochastic gradient descent, right? And the core of stochastic gradient descent is calculating the gradients. But now, unlike before, we have these compositions of functions. So what to do about that? All right, so we'll talk about that, but let's set the ground for ourselves. So here We have our likelihood. We want to maximize likelihood or minimize negative log likelihood. So here we just have likelihood, which is log probability. And here we have this is a little bit maybe now unusual way of writing this. This is the probability that the label is the I star, and this is the index of the gold label. So the probability of predicting the gold label, the ground truth label, the label that a human annotators has said that this instance correspond to, that's going to be equal to logarithm of the softmax of the output matrix times z, where z is that transformed vector, so g of w1 times f of x. But this gives us a vector, and we need to find the value in that vector corresponding to the gold label. And the way you can write this down is to multiply that vector with the vector that has zeros everywhere except at the position, where at the index of the gold label where we have 1. Writing this together is the same as picking the value in your softmax vector where that corresponds to gold label. So yeah, logarithm of the probability is defined by the value in the softmax, and we need to pick the one that corresponds to the gold label. So I think this now maybe answers your question, like seeing logistic regression and seeing the loss function written like this.
A little bit, like, well, once you do like the gradient, does it not depend on what your classification is, like the true classification?
Yeah, so you will again, I don't know from the top of my head, but I believe then you will derive gradients for corresponding to a specific label, not for, all of them. And yeah, we would, so sorry, just trying to think out loud here. We are going to have a loss function, and from that loss function, we are going to calculate our gradients. Yeah, I can't now mentally map like what we exactly is the issue here. So maybe we can talk later about this. Yeah. Yeah, I can't now think of it in my head on fly. Okay, and if we apply this logarithm to this what's going on here, and if we do that, which we won't do now, we will get this kind of equation. And this is our multi-class logistic regression. And the gradient with respect to the output matrix can be computed the same as we have done it for the logistic regression. I didn't really derive these things for the multi-class version. It's all about generalization from binary to more classes, and there isn't anything super extra special over there. I didn't find that going over that is be the best use of today's time. But the point is that you can do that if you, with respect to your now nonlinear features, your features Z, which are the nonlinearity applied to the product W1 times f of x. But what about the gradient of, and this is a mistake over here, let me just correct it. Okay. So what about the gradient with respect to the weights that we have used to transform our space? And here we are going to use backpropagation. Again, excuse me, I just don't want to forget to correct this later on. And here we are just going to apply the chain rule, which means that if we have our derivative with respect to our log probabilities, with respect to these weights W1, we are going to first calculate our derivatives with respect to Z, which is this hidden feature, and the derivatives of Z with respect to that W1, and there is a direct correspondence, right? Here again, we will need to take the derivative of our nonlinearity function with respect to A, where A is W1 times f of x. So what you're basically doing is going back through your layers and collecting the derivatives on fly and multiply them using the chain of rule. And backpropagation, I do not want to go into ins and outs of it because it's a huge topic. It started before the neural networks. It has a rich history, has rich mathematical interpretation, and it's widely important. But for us now, it's just important to know that what we are doing is using this chain rule, calculating the derivatives as we go back. So this will be also referred to as a backward pass, opposite to our forward pass, where you go back through your layers and collect the derivatives. And then with the stochastic gradient descent, you are updating your weights with those derivatives. Excuse me. And maybe a question you have in mind is every time we define a neural network, we now need to derive these derivatives by hand, such that we can actually, write in our code the formula for derivative that's gonna calculate it, given our data. And imagine now having, hundreds of layers. That can be a scary idea to have in mind. So the good answer I have for you is that we are never going to calculate these derivatives ourselves by hand. And if you take deep learning course, probably your instructor will force you to do it once to get a sense of like what is happening. But we will use frameworks that will do this for them, and they will have something called AutoGrad that does these derivations for us. Frameworks that are used commonly are PyTorch and TensorFlow. In research, we more often use PyTorch because it's slightly more flexible, it's very open source, and it has richer community. TensorFlow is, I heard, has been, at least for a while, used extensively in more industry because it has nice properties for distributed training of models, but I think these two are used interchangeably in the industry as well. I highly recommend that you check this 60-minute blitz to get a little bit more familiar with PyTorch. There is also a lecture from our Utah's machine learning course where the whole lecture was dedicated to a PyTorch tutorial. If you want to do anything with neural networks, this is simply a must to kind of get to know a little bit more. And this is, code for on PyTorch that basically does this forward and backward pass. So you import your Torch library, and Torch has already some pre-trained models. So here, this is not a feed-forward neural network. This is a deep convolutional neural networks. You don't need to know what these are. I just wanted to use a, quick code to show you here. So this is just loading this model. You have some data, you have some labels. Here you have just a single example because these are images. You need to have like three-dimensional a tensor representing your, 3 channels in an image. And then here are the labels. There is 1,000 possibilities, 1,000 possible image classification, image classes. Again, not important for us. Don't look now into what ResNets are. Don't care about Torch Vision. It's not important. This is just an example. What's important here is what comes next. You basically get the prediction by calling your model, which is a bunch of functions composed together. You get the loss, and then you call loss.backward, and that's it. That's this function here. Torch will, on its own, using its own autogram, do that chain rules that I have described. So it will go back through the layers. It's going to calculate the derivative at each layer, and each weight in that layer will have some kind of variable where these derivatives should be stored. So as the backward is going through the layers, it's also recording what the derivatives are at each one of these layers. So when we do the optimization, and here again, we don't necessarily need to implement SGD. We just load it for the Torch Optim and take a step of the optimizer. What is happening here is then the optimizer here will go back to those variables and change their weights variables corresponding to whatever is stored in their derivative variable. So you just have at each layer, the weight parameters values, the derivative values, and when you call the optimizer, you just change weights by the gradient values. Okay, so everything is very abstract, and you don't need to do many of these things by hand, which is great. Otherwise, this would be not really fun to work with. Yeah, there is an episode of the podcast The Gradient where one of the principal engineers who has kind of driven this talked about like this initial phases of PyTorch. It's a super fun episode to just hear about how low-level things were at the time, you know, in this 2015 era, and now you get so much abstraction. So if you were doing some of these things at that time, you would deal with so many little things, and now so many things are taken care of for you. So you can, in one afternoon, you can run a classifier, a neural classifier, although you have just, you know, learned about these things. Okay, questions about these abstractions? I mean, I didn't go into details of this. We don't really have time to go over much of what there is to say about this topic. I just wanted to show that, you know, the things aren't, that the things are pretty abstract here. Okay, so once again, stochastic gradient descent. I want to remind you that here in this equation I have shown you before, we are looping over our entire training data set. And we are computing the gradients after each one of the examples and updating weights after each one of the examples. And we do not, in practice, actually, very rarely we do this. Instead, we are taking the batch of data, meaning a group of instances such as 8 or 16 or 32 or 64 or more if we can, and we are going to compute the derivatives for each one of them and average them and then make the update. So the update doesn't happen after every single example, rather after every batch size number of examples. And this is called the mini batch gradient descent. This means that when we deal with our inputs and outputs, they are not anymore, you know, before I had said that our output space is m-dimensional list. Once we start batching things, it's not going to be like that anymore. It's going to be a matrix of size, batch size, number of classes. So we are turning our vectors into our matrices, and what were matrices before will be turned into three-dimensional tensors. Almost never you work with a batch size of 1 unless you have a ridiculously large model with not enough GPU memory. So yeah, you will always see batch size times number of features rather just number of features, which was n in my illustrations before. But again, the whole frameworks we have are designed for these tensor operations. They are combined very well with NumPy, for example. So everything becomes still very similar. You just, instead of a single number, you might end up with a vector. Instead of a vector, you might end up with a matrix, but things are designed that you still can easily work with this. What is the good batch size? Yet again, this is a hyperparameter. You don't want it to be too small because of the reasons we have just said, right? You don't want to do the update after every single example. But you don't also have an opportunity to have gigantic, number of batch examples because you're going to be capped by the sizes of these matrices. If you had very, very large number for batch size and very, very large number of features, you are getting a very, very large matrix, and that you have a bunch of those then, which in each one of the layers in your deep neural network, and your GPU, your graphical card unit that you need for faster training of these things might not be able to have enough memory to store all of those values. So usually you get something like CUDA out of memory issues, they are sad, and then you decrease your batch size until you stop getting it. Other things we need to deal with are initializing our weights. Before I go into that, is this clear, the batching? again, simple idea. Okay, any other questions? Okay, so then how do we initialize our weight matrices? We are dealing with non-convex problems. So, you know, when I was showing you illustration of SGD and we had that very nice convex function, then you just go down, 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 and you end up in your minimum. That is not the case with neural networks. You have something that's very, very curvy, and wherever you start really will affect your learning. If you ended up in a very bad, let's say, valley that's completely flat, you will not learn anything because you are stuck in that, you know, plateau. So initialization really, really matters because we are dealing with non-convex problems. What will happen if we initialize our weights to 0, like we did with logistic regression? Like, what would happen with if W1 is all 0? I don't hear you. Was maybe exactly, and hardly useful then, right? Because what we can do with every example represented with the 0 vector. And then there are things like saturation of gradients. I have said before, I don't want to go now into ins and outs of nonlinear functions, but the gradients here are going to be 0. Or if you have a ReLU, that's identity function, they can become what we would say they explode. They become too large. So the choice of nonlinearity also has the effect on our gradients. They can become either too small, not changing our weights too bad, or they can become, you know, enormous, changing our weights too much. So yeah, that nonlinearity also has an interplay, like our weights and nonlinearity are combined together, so that's going to matter as well. So without ton of motivation, I'll just drop this. What has turned out to be really good option is this Xavier-Glorot initializer, which is basically drawing values uniformly, but not from any range. Rather, you give this specific range, which is determined by what's the dimension of the vectors that are, that are given to your layer, and the size of the output vectors. Now this idea of like a vector is in and out might be a little bit confusing. What this means are basically these, when you have the vector matrix multiplication, you have certain vector size you begin with, right? Like we had n-dimensional vector, and then we ended up with d-dimensional vector. Here, n is in dimension and d is out dimension, or m and n here. So it's going to be determined by that. Yeah.
Do you know why there's a 6?
Oh, I knew at some point. Now I completely forgot. There is an explanation. It's not random. I mean, obviously it's not random. Like, why wouldn't they put 1 then? Yeah, I can't remember what exactly there is, but I'm sure there is an explanation in the deep learning book. So I can check it out. And I keep forgetting to do things for you when I say I will. So if you can't find it and I don't share it with you, please remind me. Yeah, there is an explanation for that. Okay, I think in the end it's all about the ratios, but yeah, I don't want to guess now. So yeah, this is basically what you would use to initialize your weights. And I think this hasn't changed much since this was introduced. Now, I mentioned, although I didn't put it in the slide, there are also these exploding gradients, and our network can become, we might choose too many parameters for what we really need for our problem. So we might have a problem of overfitting, which, just to remind you, means that your model is over-parameterized, meaning if we are talking about polynomials, it has all those crazy fluctuations, and it can have a lot of flexibility of what kind of problems it can solve. And you have training examples, And maybe one example is outlier, and now your model, which has an ability to do that, go crazy and totally fits that one outlier. But then when we see new examples, we won't see anything around those outliers, and maybe those, where the fluctuation happened. If we have new examples somewhere there, we will have an error now because the curve is way higher than it should be. And this was something we called overfitting, and regularization is idea of how to deal with this problem by basically decreasing the number of parameters the model uses to solve its problem. So for example, L2 regularization, I don't know whether I have mentioned it, you might have heard it before, is the idea where you add to the loss function the L2 norm of your weights, and you also minimize it, which means that the weights can't become too huge, which is what would cause a polynomial to have this huge fluctuation. And with neural networks, another idea, had been proposed, which is to randomly zero out parts of your weight matrices during training. So every time you do a forward press, you just randomly, for that batch of data, you randomly zero out some of the weights. And what this achieves is that the model does not over-rely on certain weights too much. And then at the test time, you use the whole network. You are not using this partially used network. And this has been shown to regularize neural networks pretty well. And I think, yeah, we still use these things, but we don't really, again, because we deal with pre-trained models, they have certain, they have already been trained, and if these things are not super important, we won't have these issues with them. Questions about dropout? Yeah, and for the exploding gradients, which I didn't put on the slides over here, there is also something called gradient clipping, where you are calculating the gradients, and if their norm is higher than whatever you set the gradient clipping hyperparameter to, you then threshold it to that value. So if the gradient the norm was 10, but you said it should not be higher than 6, you will cap it to 6. And in this way, you kind of deal with these exploding gradients, which also have connection with the overfitting. Okay, and this brings me to the last thing I want to talk about. So I keep mentioning stochastic gradient descent, of course, massively important, but we don't really use its most standard form ever in NLP. We use an optimizer called Adam or some other alternatives to SGD. The reason why we don't use very often just SGD is because it has been shown empirically over and over that setting the right learning rate is the most important, one of the most important hyperparameters in your machine learning design. And we know that if we take something that's too small, we might never come to the right value. Or if we use something that's huge, we might even have those huge swings that brings us to a whole other side of the valley. So it really matters what the learning rate is. The first side extension that has been proposed is this idea of the momentum, where you now suddenly care about what are the directions you have previously taken. And the idea is that you might want to be influenced by the directions you have taken before. And this is because some of these, when we think about our loss spaces, now we work in a higher dimensional spaces, so it's even a little bit hard to start to visualize these things, but they might have these curvatures. And these curvatures can kind of derail your gradient descent by not taking what was previously steepest and would truly be, if you just keep taking that direction, you will end up to a great spot. But there is this small curvature, and now locally, where the steepest descent is not that previous direction, rather something completely different. but it brings you to a bad space, and you don't want to just be like greedily, locally, totally digress into bad spot. So momentum is another hyperparameter, which basically says how much do you want your update to be affected by the directions you have taken previously. If you set it to something high, you will be affected a lot. If you set it to 0, you get stochastic gradient descent. So very low values means you don't really care that much. The issue with momentum is that you introduced yet another hyperparameter, right? So it kind of, the idea is nice, but by the hyperparameter tuning, not so much. And this kind of brought another idea, which are adaptive learning rate algorithms, where you believe that there are certain, the directions of these sensitivity are axis aligned, meaning that if you have certain coordinate systems, they are going to be basically sensitivity will be happening in those directions. And the idea is to use a separate learning rate for each one of your parameters, so for each one of your weights. And you automatically adapt these during the training of your neural network. So instead of having one learning rate, you have a vector or a matrix, whatever it is. So you have multiple learning rates, and all of them start with the same value, let's say 0.1. And then as you are training your neural network, these are going to be changed in some way. I didn't bring you equations here because I don't think that level of detail is necessary for us, but they are going to be changed in some way. So you might plot also how your learning rate changes with training of your neural network. And ADAM is one of these adaptive learning algorithms which kind of takes this idea and also combines it with this, momentum idea. And it's the most used algorithm in NLP for training, I believe, in other modalities too. And I think this paper might be the most cited paper in machine learning, which makes it the most cited paper that exists in the world. It has some ridiculous number of citations because ADAM is really the optimization algorithm today. So, we will rarely use, where did I use it? Here, Torch Optim SGD, but luckily for us, ADAM will certainly be implemented as well, and it's probably just torch.optim.adam. So not much changes for us, it's just calling another function. And since I have time, there is this one term in the ADAM that's called, it is parameter that checks the gradients in the beginning of the training and does some correction of them. And when BERT, which is a model we are going to, vitally important pre-trained model we are going to talk about later, when it was released, researchers noticed that it's really unstable. So if I use, there is still randomness with models, so we need to choose how we initialize these things, which are determined by random seeds. If you use different random seeds, we had seen widely different results. And there were like a number of papers that have shown that BERT is really unstable, which was really, really unsatisfactory given how important it is. In only years after someone had discovered that the original implementation had changed the ADAM algorithm, and that they changed that, they removed that bias correction term that serves for looking at the initial gradients when they are noisy. And that made the whole training later on noisy and unstable. And it's kind of, for me at least, it was kind of strange to hear that someone would take something in the most important algorithm that we have in this thing. And it turned out that it was really hard to distribute it over multiple GPUs. So engineers decided, this is not really important, and removed it. And it turned out to be massively important for the stability. So sometimes knowing these low-level details, can be really helpful, because then okay, it seems like a number, like a single number, how important could it be? But then it turns to be like really important. Okay, so that's it for today. Yeah, don't forget the homework for tomorrow, and see you next week.